So students, we are discussing the combination of reactors, and I told you that what various combinations are possible in series and parallel. So starting we did the starting with the reactors connected in series, and in that case also I started with the CSTRs connected in series. So I already explained that when the CSTRs are connected in series, then how you have to analyze, how you have to write the design equation in terms of concentration, in terms of conversion, which equation is valid for CVRS, which equation is valid for VVRS, this we discussed. I also explained that if we assume a first order reaction, if we assume that all the volumes of the reactors are same, and we also assume that the temperatures are same, so rate constants are also same, the reaction is CVRS. In that case we also derived one expression, तो वो expression आपको याद भी रखना है. That expression is only valid for the particular case, but questions आ जाते हैं और वहाँ पे questions में number of CSTRs को 5 या 10 भी किया जा सकता है, because we have a direct formula. For first order we derived some things, we have a direct formula for that, right? So now let us proceed. मैंने आपको बताया कि मैंने आपको quantitative analysis तो दे दी, but we want some qualitative analysis right now, कि how to analyze the things, that what is happening in that combination of reactors, and how to analyze the things on Levenspiel plots also. So let us consider two CSTRs. आप तीन भी कर सकते हैं, तो हम लोग let's take the case of two CSTR connected. And as I explained you already that it is already a complex discussion, so I won't make it further complex by assuming a VVRS system. So let us assume CVRS system only. So suppose this is the scenario. Initially I took 3 CSTRs for doing all those design equations, but right now we are taking only 2 CSTRs in series. So, and as I explained that conversion is based on reference state, और मैंने आपको ये समझा दिया कि if you are changing your reference, then how to deal with the things. But I also explained that in GATE exam, the reference point chosen for defining the conversion, or you can say that the conversion is 0, is taken only at this point. और सारे कन्वर्जन आपको इसी के हिसाब से रिपोर्ट करने हैं, और सारे कन्वर्जन आपको इसी के हिसाब से दिए भी होंगे. सो अब बार बार ये रेफरेंस स्टेट को चेंज नहीं करेंगे, वो बस एक अंडरस्टैंडिंग को डेवलप करने के लिए था कि व्हाट इज द मीनिंग व्हेन आई से दैट रेफरेंस स्टेट डिपेंड्स अपॉन द कन्वर्जन डिपेंड्स अपॉन द रेफरेंस स्टेट. नाउ x is equal to 0, हियर आल्सो वॉल्यूमेट्रिक फ्लो रेट इज न्यू नॉट, concentration is CA1, conversion is XA1, volumetric flow rate nu naught, concentration CA2, conversion is XA2. This is the scenario, right? Now what about the volume of these two reactors? Suppose I am taking different CSTR volumes, volume V1 and volume V2. अब इनकी क्वालिटेटिव एनालिसिस करनी है कि इनको रिप्रेजेंट कैसे करना है ऑन द लेवेंस्पील प्लॉट्स, और फिर द टाइप ऑफ वॉल्यूम, किसका वॉल्यूम ज़्यादा होगा, किसका वॉल्यूम कम होगा, किस फैक्टर्स पे सारी डिपेंड करेंगी चीज़ें, इसके बारे में बात कर लेते हैं, ठीक है. सो हाउ टू रिप्रेजेंट इट ऑन द लेवेंस्पील प्लॉट्स. यू नो दैट in the discussion of Levenspiel plots, I explained that 1 by rate versus conversion plot, 1 by rate versus conversion plot, the area is an indication of volume, right? The area is an indication of volume. Now when CSTRs are connected in series, this is the plot, and you know that this plot is for a specific order. So अगर कई बार मैं नहीं भी लिखता हूँ कि this plot is for a specific order, you should understand कि it is not a you can say a general plot of any reaction. Depends what is the order. I hope you remember that this kind of plot was only there for n greater than 0. For positive orders we had this plot. Now you know that for a CSTR, how to represent a CSTR on Levenspiel plots? By area under the curve or by completing the rectangle. According to the design equation of CSTR, a CSTR is always represented by completing the rectangle. Now let's do that. Suppose from 0 to XO1, this is the point, XA1, right? And from XA1, the final conversion, XA2, suppose that is the point, XA2. So how to represent it? XA2. I'm going to complete the rectangle here. So one rectangle and the other rectangle. This is how you represent the two CSTRs, or the volume of the two CSTR used here in this case, right? So let us shade कर देते हैं. This is the area representing the volume of first CSTR, and this is the area representing the volume of second CSTR. Definitely if you add more CSTRs, I can represent the volume of the two reactors like this. And it is not exactly volume, you know that it is the indication of volume, right? Because what was this value? This value was equal to tau by Ca naught. And tau is by Ca naught is not volume. Even tau is not volume. So it is not the value of volume, it is the indication of volume. Now when CSTRs are connected in series, they can be represented like this on this Levenspiel plots. Right. One more thing. Now there comes a case that if you increase the number of CSTRs, then what happens? If number of CSTRs connected in series, number of CSTRs connected in series is increased. If number of CSTRs connected in series is increased, then definitely you can add more and more rectangles, right? And then that can be represented on the Levenspiel plots. Let's see how. I hope this graph is visible to you. Again, the graph is between 1 by rate versus XA. And suppose what I am doing, I am continuously increasing the number of CSTRs. And suppose I have a number of CSTRs, not 3, but 10 or 15 CSTRs connected in series. And the graph is like this. Let me make the graph a little bit curved so that right, that is the graph. Now suppose I have a number of CSTRs connected in series, then how I am going to represent that? This is the rectangle, the first rectangle for the first CSTR. Suppose I am taking 7 or 8 CSTRs so that I can represent here. This is the second rectangle, second CSTR, representing the second CSTR, third rectangle, representing the third CSTR, right? Like this, you can add a number of CSTRs and then that can be represented on the Levenspiel plot. So when the CSTR is connected like this, then that can be represented on the plot. आप एक एक करके rectangles बनाते जाओ. And please note that for representing the CSTR, I hope आपने लेक्चर ध्यान से देखा, अगर नहीं देखा तो दोबारा उसको देखो कि CSTR is represented by completing the rectangle according to the final conversion, right? Let's take one more CSTR like this. So if a number of CSTRs are connected like this, you will be getting this kind of Levenspiel plots. I hope it is visible to you. Now say, let's suppose if number of CSTRs is series is increased, how many CSTRs are there? 1, 2, 3, 4, 5, 6, up to 6. Then it is represented like this, right? Also, suppose infinite number of CSTRs. Now, of course, infinity cannot be reached in practice. Suppose infinite number of CSTRs are connected. Infinite number of CSTRs are connected in series. Then see how the representation looks like on the Levenspiel plot. I asked you one question in the previous lectures, that in which case a CSTR can behave like a PFR. Now I'm going to answer that question. And the second one also I will answer after a while, maybe in the next lectures. So this is the graph, 1 by rate versus conversion. And what is the meaning of infinite? Means a large number of CSTR. In practice, infinite number of CSTRs can be reached if you have 25, 30 or 40 CSTRs connected in series. So suppose infinite number of CSTRs are connected in series, then how you are going to represent that? Suppose it's something like this, a number of CSTRs, you have a number of CSTRs like this. A number of CSTRs connected in series. Then how they can be represented? The area of the rectangle will be completed like this. A number of CSTRs are there. Of course, I cannot show infinity here, so I have to show few numbers because infinity cannot be shown on this graph. तो कुछ ना कुछ number तो मुझे दिखाने पड़ेंगे, है ना? I'm trying to show as many number of CSTRs as possible here. So, a number of CSTRs like this. And you can see that if I complete the rectangle here, everywhere if I complete the rectangle, and let me shade these rectangle first. So this was the first and then second one, third one, a little bit above the graph also. Now can you see that this area is almost same as the area we get for a PFR, because the area of the rectangle, if you combine all the areas of this rectangle, it is almost similar to the area under the curve. I hope you are getting this point. The area of the rectangle of all, of course there is some area above the graph which is not there in case of PFR, but we are getting that area because the number of rectangles which I am making here is finite. If you take infinite number of CSTRs connected in series and then you complete the rectangles, then definitely you are going to get exactly the same area which we get for PFR. And this is the case when CSTR, of course a single CSTR cannot act like a PFR. Don't think about that. A single CSTR cannot act like a PFR. But if you combine a number of CSTRs connected in series, and if you reach infinity, then that is going to behave exactly like a PFR. Because what was the Levenspiel plot for a PFR? For a PFR, the plot was exactly like this. Area under the curve. Now this area, this plot is similar to the plot of a PFR. What is the plot of a PFR? You are going to get the area under the curve. It means a combination of CSTR, ऑफ कोर्स एक चीज मैं आपको बता दूं कि सिंगल CSTR कभी भी PFR की तरह एक्ट नहीं करेगा. कभी भी आपसे कोई पूछे कि CSTR कब PFR की तरह एक्ट कर सकता है, यू शुड से दैट व्हेन CSTRs आर कनेक्टेड इन सीरीज दे एक्ट लाइक अ PFR. बट लेट मी मेक दिस पॉइंट फर्दर क्लियर. Suppose infinite number of CSTRs are connected in series, then you are getting this kind of design curve or Levenspiel plot. A combination of CSTRs in series act like a PFR. Act like a PFR if the number of CSTRs in series is infinite. मतलब जब तक आप इन्फिनाइट CSTR कनेक्ट नहीं करते हो तब तक तो वो आइडियल PFR नहीं बनेगा. बट डेफिनेटली लेट मी अगेन क्लैरिफाई फ्यू थिंग्स हियर. If you are connecting 2 CSTR or 3 CSTRs, in that case, there are two extreme behaviors. I told you that there is one extreme at single CSTR and then there is PFR. If you are combining 2 CSTRs in series, then you are shifting the behavior from ideal CSTR to a little bit closer towards the PFR. मैं नहीं कह रहा कि जैसे ही आपने 2 CSTR लगा दिए वो PFR बन गया, ऐसा नहीं है. If you are combining 2 CSTRs in series, you are moving a little bit closer to the PFR behavior. मान लो वो this end of the board is the CSTR behavior and this end of the board is the PFR behavior. The moment you connect, you combine 2 reactors, 2 CSTR in series, now the system, the entire system moves a bit closer to the PFR. You connect 3 CSTR in series, तो जैसे जैसे नंबर ऑफ CSTR आप बढ़ाते जाओगे आप PFR बिहेवियर के, और क्योंकि यहां देखो नाउ दिस थिंग आई हैव 2 CSTR कनेक्टेड इन सीरीज, this area is significantly different than the area under the curve. So the system of 2 CSTR connected in series is little bit closer to the PFR behavior. The system of 6 CSTR connected in series is further closer to the PFR behavior, and the system of infinite CSTR connected in series is exactly like the PFR behavior. फिर से एक और पॉइंट यहाँ पे क्लियर करते हैं कि जब आप 2 CSTR को सीरीज में लगा दोगे तो ऐसा नहीं है कि इंडिविजुअल CSTR PFR बन जाएगा. नो, इंडिविजुअल CSTR इज स्टिल एन इंडिविजुअल CSTR. अगर आप 2 CSTRs को सीरीज में कंबाइन कर देते हो, then still individual CSTR is behaving like a CSTR. There's nothing happening, there's nothing different happening in the reactor. But the entire system of 2 CSTR is now behaving like a PFR. Okay, let us write these points. A combination of CSTR in series act like a PFR if the number of CSTRs in series is infinite. That is one point. As the number of CSTR connected in series, as the number of CSTRs connected in series increases. So I have explained it from this to this to this, the number of CSTRs connected in series increases. As the number of CSTRs connected in series connected in series increases, the behavior of the system, please note I am not writing behavior of the CSTR. CSTR का behavior तो CSTR का ही behavior रहेगा, but the system, what is the meaning of system? System means this entire system. System means this entire system. So as the number of CSTRs connected in series increases, the behavior of the NCSTR system, N means the number of CSTR, the behavior of the NCSTR system, I'm calling this entire CSTR system as NCSTR system, becomes more closer to PFR. Becomes more closer to PFR. That is the point. This point is very important. So कई बच्चों के दिमाग में confusion रहती है कि सर मैंने 3 CSTR लगा दिया वो PFR बन गया. It's not like that. If you are having 3 CSTRs connected in series, the first point that each individual CSTR is still a CSTR. The second point, if you compare, if you say that the entire system of the 3 CSTR has now started behaving like a PFR, closer to a PFR, not exactly a PFR. Exact PFR की तरह कब behave करेगा? When you have infinite number of CSTRs connected in series. That is another important point. Now let's talk about the next point. It says, what is the comparison of CSTR and PFR? I have done extensive discussion about the comparison of CSTR and PFR. You know that, I hope you remember. What was the discussion of PFR and CSTR? PFR and CSTR comparison, what was that? I hope you remember that for n greater than 0, PFR is selected. N greater than n equal to 0, both are equivalent, and n less than 0, CSTR is selected. That was the selection of reactor topic. So selection of reactor में इसको काफी डिटेल में डिस्कस कर लिया. Now what I'm saying that a system of CSTR connected in series is behaving like a PFR, behaving closer to the PFR. Fine. So I'm saying that this system NCSTR in series is behaving like a PFR. What is this? It's behaving like a PFR. Of course, it will be exactly like PFR when n is infinity. But if n is not infinity, at least, agar n is finite, suppose, at least it is more PFR than a CSTR. Getting my point? Agar n finite be, in this case also, in this case, n is not infinity, but the behavior of the system is more closer to the PFR than a single CSTR. So, right, so PFR and CSTR, NCSTR connected in series, I am treating it as PFR. Now the same comparison can be done. Now what is the comparison? Comparison of a single CSTR, comparison of a single CSTR and NCSTR. ये कोई नया कंपैरिजन नहीं है, आप बस ऐसा समझ लो. Now I am treating the NCSTR as a PFR. So all the points remain same. All the points of comparison remain same as we have discussed in selection of reactor. Right now I am giving you a condition when the NCSTR system is behaving like a PFR. So a combination of CSTR in series act like a PFR if the number of CSTRs in series is infinite. So comparison of single CSTR and NCSTR. क्या compare करना है देखो. There is a CSTR of volume 10 liter. That is one case. And then you are comparing it a number of CSTRs of volume 10 liter, 10 liter, 10 liter. ये compare करना है क्या? Connected in series. Are we comparing this case? Definitely no. कई बच्चों के दिमाग में ये रहता है, ये this is not the comparison. How you can compare these things? This comparison is not justified. ये तो भाई इसके साथ में आपने justification नहीं किया ना. You are taking a single CSTR of 10 liter and you are taking 3 CSTRs of 10 liters. Definitely it is better. There is no case when this is not better. Whatever be the order, this will be better than this. बिकॉज यू आर गिविंग मोर वॉल्यूम एंड मोर वॉल्यूम लीड्स टू मोर कन्वर्जन. तो ये कंपैरिजन नहीं करना है, ये दिमाग से. अगर ये वी आर नॉट कंपेयरिंग सिंगल CSTR एंड CSTR ऑफ द सेम वॉल्यूम. व्हाट वी आर डूइंग, वी आर, भाई अगर आप कुछ कंपेयर करोगे तो आप सेम टाइप की कैटेगरी में कंपेयर करोगे ना. इफ यू आर कंपेयरिंग द थिंग्स, ऐसा नहीं है ना कि आप मतलब एक खरगोश है, एक खरगोश को ले रहे हो और दूसरा मतलब किसी एक्वेटिक एनिमल को साथ में ले रहे हो, उनको बैठ के कंपेयर कर रहे हो, है ना. यू कांट कंपेयर two persons of different abilities who are expert in their different kind of fields. उनको compare नहीं कर सकते. When we are comparing, then this is not justified. We can't compare this. Definitely आप बोलोगे sir, yeah, you can calculate of course, and calculations can give you any result. So let's not compare this. What we are comparing that there is a single CSTR of 10 liter, and then there are combination of CSTR such that the total volume is 10 liter. And what is the total? It can be 5 liter and 5 liter CSTR. You combine them in series, or what you can do that 2 liter, 2 liter, 2 liter, 2 liter. This kind of comparison we are doing, right? Or you can have 3 liter and 6 liter like this. We are doing this comparison. We are not doing this comparison. Don't do that. We are doing comparison of a single CSTR and multiple CSTR connected in series such that their total volume remains same. Getting my point? Now I am saying that when CSTR are connected in series, their behavior is more closer to PFR as compared to single CSTR of same total volume. I hope the idea is clear. And let me write this point also. When CSTRs are connected in series, when CSTRs are connected in series, I'm not saying they become PFR, they are more closer to PFR, क्योंकि PFR तो केवल इसी केस में बनेंगे. ये बात बहुत क्लियर होनी चाहिए. इनफाइनाइट वॉल्यूम, इनफाइनाइट नंबर ऑफ CSTRs होंगे तभी उस केस में PFR की तरह बिहेव करेंगे. When CSTRs are connected in series, then the behavior of the system, when CSTRs are connected in series, then the behavior of the system becomes more closer to the PFR. ये पॉइंट्स मैं पहले भी लिख चुका हूं, बट एक बार ये पॉइंट एक्सप्लेन कर रहे हैं कि किस तरह से कंपेयर करना है. When CSTRs are connected in series, then the behavior of the system becomes more closer to PFR, as compared to single CSTR of same total volume. As compared to single CSTR of same total volume. Single CSTR of same total volume. That is the idea here. Fine. And you know that what is the behavior of a PFR. If something is more closer to PFR, it is going to behave like a PFR. What is the behavior of a PFR? If order is 0, greater than 0, PFR gives more conversion than CSTR. I have compared this, but while comparing also I have kept the PFR volume and CSTR volume same, because अगर आप वॉल्यूम ही अलग लोगे तो ये तो injustice हो जाएगा, है ना. आप injustice नहीं कर सकते. You have to compare one thing, you have to keep other thing constants. Right now we are comparing the conversion given by these two systems, then we are keeping the total volume constant. So what is the result? Now I'm not going to derive here, definitely I can prove it graphically, but we have already done these things, right? So for n greater than 0, what we have studied? Conversion of PFR is more than conversion of CSTR. I hope you remember this. Conversion of PFR is more than conversion of CSTR of same volume. I hope you know this. And what is PFR? The behavior of n CSTR is more closer to the PFR as compared to single CSTR. So that is the result. If order is greater than 0, then CSTRs combined in series are definitely going to have more conversion than a single CSTR of same total volume. This point is important here. So don't miss it. Of CSTR of same total volume. Of same total volume. What else? Next is n is equal to 0. What we have studied that for zero order reaction, conversion obtained in a PFR is equal to conversion obtained in a CSTR if they have the same volume, right? So in this case, conversion obtained in a system of NCSTR, it is behaving like a PFR, more closer to PFR, should be equal to the conversion obtained in a single CSTR of same total volume. I am repeatedly writing this because अगर नहीं लिखूंगा तो आप अपनी मर्जी से कुछ समझ लोगे और वो गलत कॉन्सेप्ट लेके ही चलते रहोगे, ठीक है? तो अपनी मर्जी से कुछ नहीं समझना है, ठीक है? जो समझा रहा हूं बस उसी को समझो, अलग से एक्स्ट्रा कॉन्सेप्ट खुद से नहीं बनाने हैं, अपने अपने कॉन्सेप्ट नहीं बनाने, ठीक है? सो फॉर n इक्वल टू 0 कन्वर्जन ऑफ PFR इज कन्वर्जन ऑफ CSTR. For negative order reactions, what we have studied, that conversion obtained in a PFR, I have proved these things by using the you can say the Levenspiel plots. Conversion of PFR is less than conversion of CSTR. Therefore, for negative order, conversion obtained in NCSTR is less than conversion obtained in a single CSTR of same total volume. आपको ये अलग से नहीं याद रखना है. No need to remember these things separately, right? If you remember that NCSTR behavior becomes closer to PFR, then you automatically remember this because आपने CSTR और PFR के लिए अलग से कर रखा है in a single CSTR of same total volume. So this is the idea. This is the comparison of NCSTR connected in series and single CSTR connected in series. Okay, one more point I would like to mention here, that this can also be done by keeping the conversion fixed and the volume. Then we are going to compare the volume. So let me write here. That is another way of understanding the same thing. What we have studied, that for a reaction having order more than 0, PFR requires less volume than CSTR for same conversion, right? So same thing can be written here also. आप इसको बस एक बार लिख लो क्योंकि देखो ये एक ही बात है, बस यहाँ पे एक नई चीज जो मैंने आपको ये बताई, दैट इज कि जब आप CSTRs को सीरीज में कनेक्ट कर दे तो उनका पूरा बिहेवियर PFR के क्लोज हो जाता है. और वो बताने के लिए किस चीज का यूज किया मैंने, द यूज आई एम यूजिंग दिस थिंग, है ना, द लेवेंस्पील प्लॉट्स यूज कर रहे हैं, राइट? सो फॉर n greater than 0. Now let us compare the volumes. For n greater than 0, what we have studied? We have studied that volume required by a PFR, because PFR was suitable, right? And suitable means volume should be less, is less than the volume required by a CSTR for same conversion. So what is the meaning of PFR here? Volume of NCSTR. And please note, when I am talking about volume of NCSTR, I am talking about combined volume, means V1, V2, V3, everything, okay? Volume required by NCSTR is definitely less than volume required by single CSTR for same conversion. This is how you can make more and more conclusions from same discussion. तो मैं हर conclusion भी आपको लिखवा रहा हूँ ताकि फिर आप ये ना सोचो कि सर कॉन्सेप्ट तो डिस्कस हो गया, अब इसके कंक्लूजन्स कहाँ तक पढ़ने हैं कहाँ तक नहीं पढ़ने हैं. ऑल द कंक्लूजन्स ऑल्सो आई एम डिस्कसिंग हियर. सो n greater than 0. नाउ फॉर n equal to 0, volume required by a PFR is definitely equal to volume required by a CSTR for same conversion. Fine. So same goes with the NCSTR connected in series. It means that the total volume of NCSTR connected in series is equal to the volume required for a single CSTR for same conversion if order of the reaction is equal to 0. Similarly, if order is less than 0, in this case, volume required by a PFR was more and the PFR was not accepted, the PFR was rejected. In both the discussion, PFR will be rejected. Either you compare with respect to volume, because volume should be less for accepting the reactor, and if you compare with respect to conversion, because conversion should be more for accepting the reactor. So PFR was greater than the volume of CSTR. Adding a point for same conversion. So same point I can write here for the case of multiple reactors connected in series, that volume required by the system of NCSTR will be definitely greater than the volume required by a single CSTR, and therefore for same conversion. Fine. Question आपके पास इसमें theoretical आता है that there is a first order system, or suppose Okay, first order system, you are having which of the following configuration is best for getting the higher conversion. So you can have a single CSTR, you can have CSTRs connected in series, 2 CSTR connected in series, 3 CSTRs connected in series. Getting my point? So this is the idea here. So I hope this idea is clear. This is one more conclusion of combination of reactor. मैंने आपको बताया कि qualitatively analyze करेंगे, and of course whatever results I am giving you here, they can be 100% they can be proved by taking any example, any numerical example. You can frame numerical example by yourself. I am going to take some examples. So you can frame numerical examples by yourself, and that can be proved that these things can be proved here, right? पर ये बात अभी भी मैं आपको बता रहा हूँ कि ये पॉइंट जो यहाँ पे लिखे हैं or the points which I am writing here, no need to remember them separately. These are not new things we have already done here. Now whatever I have discussed so far, what is the new thing that I have discussed? The new thing is the NCSTR, when they are connected in series, the system behaves closer to the PFR. Now let us move out of this topic, out of this discussion now. Now still we are discussing series combination of CSTRs. इसमें काफ़ी कुछ डिस्कस करने के लिए, आप जितना डेप्थ में जाना चाहोगे मैं उतना डेप्थ में ले जाऊंगा, और काफ़ी कॉन्सेप्ट है यहाँ पे, ठीक है। लेकिन सारी चीज़ें आप लेवेंस्पील प्लॉट से डिराइव कर सकते हो, लेवेंस्पील प्लॉट से एक्सप्लेन कर सकते हो. सो आई वुड सजेस्ट यू हैव अ क्लियर अंडरस्टैंडिंग ऑफ द लेवेंस्पील प्लॉट्स. व्हाट आर द प्लॉट्स, किसके किसके बीच में प्लॉट बन रहा है, एरिया कैसे सिलेक्ट करना है. अगर नहीं है देन गो थ्रू द प्रीवियस लेक्चर्स. स्टिल इफ यू आर नॉट गेटिंग हाउ टू ड्रॉ द एरियाज, how to draw the area of rectangle, then you can always ask in the doubt section, right? So let us now discuss one more thing. That is when CSTRs are connected in series, fine, that they are going to give you more conversion than the single CSTR if the order of the reaction is more, right? Order of the reaction is more than 0, of course. But there is one more question. There is one more question. That suppose I am having two reactors. Two reactors having volume V1 and volume V2. They are having different volumes connected in series. Fine. Different volumes are there. They are connected in series. Now how they should be arranged? Getting my point? I'm talking about arrangement. How the reactors should be arranged so that they are giving you higher conversion. देखो जब भी मैं आपको कोई पॉइंट ऐसा बताता हूं कि this is giving you high conversion, automatically you should understand that should require less volume. ये पॉइंट मैं बार बार नहीं लिखूंगा. देखो मैंने अभी दोनों पॉइंट्स आपको लिखवा दिए. एक ही समझो, if I am saying that keep volume fixed, this case, any case is giving you more conversion, then it automatically means if you fix the conversion, then that particular case will require less volume. Because I told you that arrangement, that reactor is selected which is giving you more conversion or it is requiring less volume. तो जब मैं कोई चीज़ें कन्वर्जन के टर्म्स में आपको बताता हूँ तो वॉल्यूम के टर्म्स में आपको खुद से समझ लेना है कि डेफिनेटली ठीक है. अगर सर ने ये बताया कि इन दिस केस आई एम गेटिंग मोर कन्वर्जन फॉर अ गिवन वॉल्यूम, इट मीन्स इन दिस केस इट विल रिक्वायर लेस वॉल्यूम फॉर अ गिवन कन्वर्जन. ये ऑटोमेटिकली अंडरस्टैंड करना है, इसको अलग से लिखवाना या अलग से आपको रटना नहीं है. नाउ लेट्स डिस्कस दिस केस. व्हाट आई एम डूइंग हियर, आई एम हैविंग टू रिएक्टर्स. ठीक है. नाउ इन दिस टू रिएक्टर्स, if I ask you that how I should arrange them, what is the meaning of arrangement? I should place this reactor first or I should place this reactor first. कैसे arrange करूं so that I get the higher conversion or so that the total volume required for a given conversion becomes minimum? That is the question. That how to arrange, you can consider this in the form of a question. How to arrange the two reactors? How to arrange the two reactors such that minimum volume is required, this is called arrangement of reactor, right? Minimum volume is required, minimum total volume is required for a given final conversion. Minimum total volume is required for a given final conversion. For a given final conversion. Again, अगर आपको ये भी सीखना है, just Levenspiel plots are sufficient. Okay, how to identify them? I'll give you, ultimately I'm going to give you something which you can remember easily and then you can easily give your answer. But उसके पीछे का जो concept है, एक बार वो concept बता देता है, ठीक है? What concept is used, that how to arrange these two reactors? Which reactor should be kept first so that there is a minimum total volume is required for a given final conversion, or maximum final conversion is achieved for a given total volume, or maximum final conversion is achieved for a given total volume is achieved for a given total volume, for a given total वॉल्यूम. एक ही बात है, मैं फिर भी दोनों लिख दे रहा हूं बार बार ताकि आपको अब ये चीज बिल्कुल समझ आ जाए कि जब मैंने ऊपर वाली लाइन बोली है ऑटोमेटिकली दिस इज इंक्लूडेड. मैक्सिमम कन्वर्जन फॉर अ गिवन वॉल्यूम, मिनिमम वॉल्यूम फॉर अ गिवन कन्वर्जन, ये दोनों एक ही साथ चलता है, ये अलग अलग बातें नहीं है, ठीक है? तो एक का क्राइटेरिया पता है तो दूसरे का क्राइटेरिया अपने आप आपको पता है. नाउ सपोज V1 and V2, so let me take here Ca0 and conversion XA is 0 here, and here it is Ca2, volumetric flow rate is constant, CVRS system I already told you, and final conversion is XAF, which is constant. But what should be the volume of these two reactors? Okay, let me clarify, let me make a correction here. How to, or let me write what should be the volume of these two reactors. Suppose इनका volume fixed नहीं है, right? I have choice that I can use any volume of reactors, but the total conversion should be XAF. What should be the volume of these two reactors? I'll come to arrangement also. What should be the total volume? What should be the volume of each reactor? What should be the volume of each reactor? Or you can say what should be this conversion? What about this conversion? This is not fixed. This is not fixed. ये तो change होगी. ये इस तरह से आपको change करना है so that the sum of these two volumes becomes minimum. That is the minimization of the total volume of reactors connected in series. Arrangement ये नहीं है, arrangement के बारे में आगे बात करेंगे. What should be the exit conversion of first reactor? Exit conversion of first reactor. Exit. Okay, let us also remove this part, otherwise it may create confusion here. Yeah, what should be the exit conversion of first reactor? आप इसको आप करेक्ट कर लो, ठीक है? फर्स्ट रिएक्टर आप इसको करेक्ट कर लेना. I'll come to that part, but right now we are discussing a slightly different case, that I have two reactors connected in series, but their volume I don't know what should be the volume, because अगर मैंने अच्छा सपोज अगर मैं इसका वॉल्यूम फिक्स कर दिया तो डेफिनेटली कन्वर्जन भी फिक्स हो गया. देन उसमें पूछना क्या है ना, what should be the conversion at the exit of first reactor? It means I don't know what is the volume of the first reactor, because if I know volume then I know conversion. So what should be the volume or what should be the conversion at the exit of first reactor such that the total volume V1 and V2 is minimized? That is the question, right? For a given final conversion. So how to represent this? You know that how to represent two reactors? But because the volume of the reactor is not known, so even the areas are not known, because the conversion of this intermediate conversion is not fixed. कायदे से समझो बात को, इसको conversion मुझे find करनी है. कौन सी? Final तो fixed है. This one is fixed. XAF is fixed. I can't change this conversion. It means if I make a plot of 1/8 versus XA, make a plot like this, and I want this much of conversion. Now nothing should change here. This much of conversion is required. Let us write this as XAF, and the axis is XA. Now this conversion is fixed, but what is this conversion? And that depends upon the volume of the reactor. The volume is not known. So suppose the volume of the reactor, let one case that the volume of the reactor is, I take the XA1 value at here. Suppose I am taking the XA1 value here. If XA or XA intermediate, you can say, is taken here, then what is the volume of the first reactor? This. And what is the volume of the second reactor? You have to complete the rectangle according to the final conversion. That is the case. This is one case. If I take the conversion here, but suppose I take the conversion somewhere here, then what is the volume of the first reactor? If I take conversion here, then what is the volume of the first reactor? See, this is hit and trial thing. मुझे conversion पता ही नहीं है, तो अगर conversion नहीं पता मतलब volume नहीं पता, तो मैं volume और ये जो triangles इनको fix नहीं कर सकता. In this case, this is the required area, right? In this case, this will be the required area. Or suppose if conversion changes further, if I say that no, conversion is this. If conversion, if you keep the intermediate conversion here, in this case, the volume of the two rectangles or the volume of the two CSTRs connected in series is going to be different. In this case, the volume is going to be entirely different. And then this. So one possibility, and there like this there are infinite possibilities. Like this there are infinite possibilities, right? You can have the intermediate conversion at this point and then the total volume of the reactor. I hope you will be able to make this graph, and then the total volume, the total volume of the reactor should be like this. You can make three different graphs, that is not a problem, but I wanted to compare the things. Okay, that is for the red intermediate conversion. But if the intermediate conversion is at this green value, then your area should be this. The green lines. So it totally depends that where are you taking the area. And then this one. So I'm making the lines very carefully so that I hope the diagram should be clear. Still, if you feel you can make different diagrams. I don't know whether it is clear or not. Let us assume you are able to understand. So you can see here what is happening here. If conversion of, now I'm not going to shade with a black color, don't worry. So if conversion of the first reactor is at this point, then this is the required total volume. Fine. If conversion of the reactor is at the green point, then this is the required total volume. If the exit conversion of the first reactor is at red point, then this is the required total volume. So what you are saying, that according to the exit conversion of the first reactor, the total volume V1 plus V2 is going to change. Now I want to minimize it. So where should be this point? Now let me make another graph. Where should be this point? Now I am not able to explain anything here. Let me make another graph, and now I am suppose that I found that conversion where the total volume is minimum. I found it, suppose, because I can't make 5-6 cases like that. Suppose I found somehow that this is XIF and this XIF is fixed. Fine. And this conversion is that conversion which is minimizing. This conversion is minimizing the total volume. Suppose I have found somehow. Then what is the criteria if it is minimizing? Then how you can find the criteria? What is the total volume V1 plus V2? The total volume is the shaded portion. This portion gives you the total volume V1 plus V2 required for the final conversion. So let us suppose this denotes V2 and this area denotes V1. Fine. And let's say that, okay, I have found the point where the total volume is coming out to be minimum. Now the shaded area will be minimum if this shaded area will be minimum if this shaded area will be minimum if कब मिनिमम होगा ये ग्राफिकली समझते हैं डेफिनेटली एनालिटिकली ऑल्सो यू कैन डू दैट दिस थिंग कैन बी ऑल्सो डन एनालिटिकली बट लेट अस अंडरस्टैंड दिस शेडेड एरिया विल बी मिनिमम इफ द rectangle let us give name to this rectangle. I'm calling this as the rectangle, this one. This is also rectangle, right? let's call it ABCD, just the name given to the, this is the point C. Let me make some empty space here so that I can make something else in that empty space. This shaded area will be minimum if the rectangle ABCD area is maximum. I hope this is not very difficult to understand. If the rectangle ABCD area is maximum. देखो अभी मैं आपको बस ये बता रहा हूँ कि आता कहाँ से है. डेफिनेटली इन गेट एग्जाम यहाँ से क्वेश्चन आया तो नहीं है, बट ग्राफिकली कुछ फ्रेम किया जा सकता है इस पर. सो ये कॉन्सेप्ट जरूरी है समझना क्या है. ठीक है. द शेडेड एरिया विल बी मिनिमम इफ द रेक्टेंगल ABCD एरिया इज मैक्सिमम. एंड व्हेन द रेक्टेंगल ABCD एरिया इज मैक्सिमम, व्हाट डू यू थिंक? व्हेन द एरिया ऑफ अ रेक्टेंगल इज मैक्सिमम, it is maximum. Now this comes from the geometry. There is nothing, no CRE involved here. The rectangle area is maximum. The rectangle area is maximum if the slope of the diagonal, if the slope of the diagonal of ABCD, what is the diagonal of ABCD? This is the diagonal. What is its slope? This height by this, right? If the slope of the diagonal of ABCD is equal to the slope of tangent drawn at C. So this is the point C. If at C you draw a tangent, that's why I made some space here. Suppose if I draw a tangent, of course I don't know where this point, because this point C can be here, here, here. So क्या करना है? एक tangent यहाँ बनाओ and then make this slope. If they are same, if they are not same, then make tangent here and compare the slope. If they are same, then fine. If not same, then make tangent here. Like this, you have to check. So when you are making a tangent here, right, the slope of this tangent and the slope of this rectangle, the slope of this diagonal of this rectangle should be same. If this is happening, then this area is maximum, this area is minimum, and then you have found the value of exit conversion of reactant A. If the is equal to the slope drawn at C. This is the scenario. अब आप बोलोगे कि सर ये क्या है, ये कहाँ से सुन लिया आपने, ये कैसे पता लगा, ये CRE का कौन सा कॉन्सेप्ट है? नो CRE is involved here, right? The only thing which is involved is the basic geometry, कि how you can maximize the area of any rectangle you can maximize. So this is the concept from geometry. Don't worry about this. Of course this can also be explained, and it is my suggestion that somehow you try to think about then from where it comes. I'll explain somehow. कभी किसी लेक्चर के बीच में आपको मैं बताऊंगा कि ये कैसे आया, लेकिन फिलहाल this slope and this slope are equal, then this V1 plus V2 is minimum, and this is the exit conversion of reactor A. Now आप बोलोगे कि sir how we are going to solve it graphically? Now definitely if this kind of question comes in the examination, then they are going to give you such a graph which can be, in which case you can easily calculate the slopes of tangent and the slope of diagonal. Suppose I am taking a first order reaction. Let a first order reaction is taking place. Let a first order reaction is taking place. And then can you make the 1 by rate versus conversion graph? Rate versus concentration or 1 by rate versus conversion graph for a first order reaction. I hope you are able to make this graph for a first order reaction. 1 by rate versus conversion. If you try to plot, it is going to give you a linear line like this. So suppose there is a first order reaction taking place in this CSTR such that the conversion, the final conversion is fixed. आप बोलोगे सर स्ट्रेट लाइन कैसे आया? अगर आप अभी तक नहीं बना पा रहे हो स्ट्रेट लाइन तो देन आपके बेसिक्स में दिक्कत है. आप वापस जाओ और पढ़ो कि फर्स्ट ऑर्डर का 1 by rate या रेट का एक्सप्रेशन क्या होता है. द ग्राफ इज अ स्ट्रेट लाइन. Okay, now XF is fixed. Now I am saying that what should be this conversion such that the total volume of the reactor is minimum. Suppose let the intermediate conversion I am taking as this. This is the intermediate conversion. Fine. And I am saying that at this point the total volume of the reactor system is minimum. So definitely if this happens, then you are going to maximize this rectangle area. And how this is maximized? What is the slope of the diagonal? This is the slope of the diagonal. If this slope and this slope are equal, then the volume V1 plus V2 is maximized. Now I'm pretty sure that if you are saying that Xi is equal to this and 0, then definitely you have some equation here. 1 by rate is equal to some equation. Some equation must be there. Right, what is the equation of this line? Can you find the equation? What is rate? Minus Ra is equal to K Ca naught 1 minus Xa. So what is 1 by rate? 1 by rate versus Xa. 1 by rate versus Xa. So suppose if this kind of reaction is there, for a first order reaction is there, what should be the exit conversion of the first reactor? That we have to find. So suppose it is Xa is there and some kind of relation is given 1 by rate versus Xa. What do you think? What is the nature of this plot? 1 by rate is your y-axis. 1 by rate is your y-axis and rate is Kca naught, right? So 1 by 1 minus Xa. So that is y and that is x. 1 by 1 minus x. No, I don't think that the shape of the curve should be like this for the first order reaction. So it would be better that you just assume a shape here, that the shape is linear. Don't do this. Don't do this, because then there will be problems in making the graph. Because if you plot 1 by rate versus Xa, then it is 1 by rate is equal to 1 by Kca naught into 1 minus Xa. So it doesn't seems that it is varying linearly, right? So that you should correct here, that don't write that it is for first order. Suppose 1 by rate is a linear curve. Now for linear curve, if I ask you that what is the value of conversion, then you are going to say that the slope of this line. And what is the slope of this line? This value you can always calculate. Suppose 1 by rate expression is given to you. Suppose I am taking this expression. 1 by rate is equal to 1 plus x. Suppose I am taking this expression. I hope now there won't be any problem. 1 by rate is equal to 1 plus x. So this scenario is there, right? Now in this case, definitely the slope of this line can be easily calculated, because what is this point? This point is Xa. So this point, what is the coordinate of this point? This is x-axis Xa. And what is y-axis here? What is the y-axis at this point? The y-axis is 1 by rate, which is calculated at XAF. So I think the point is the y-axis here. What is the equation of 1 by rate? 1 plus x. If you put x is equal to XF, that becomes 1 plus XAF. I hope there is no problem in writing the coordinates of this point. What is the coordinate of this point? The x-axis is 0. Y-axis is put this 1 plus x here. Put Xa here. The middle conversion. The middle conversion in this equation. The same y-axis is here. So it becomes 1 plus Xa. Right? I hope I'm not making any mistake here. X-axis is Xa and y-axis is fine. Right, fine. And suppose, let's write the coordinates of this line so that I can find the tangent of this also. What is the coordinate here? XAF and 1 plus XAF. Why I am writing 1 plus XAF? Because the line of this equation, what is the equation of this line? 1 plus x. So just put the value of Xa and you are going to get the coordinate. And what is the coordinate of this point? This becomes x is 0 and y is, if you put conversion is equal to 0, you are getting y is equal to 1. Fine. Now you tell me that what is the slope of this tangent? What is the slope of this tangent? The slope is y2 minus y1, 1 plus xaf minus 1 divided by x2 minus x1, that is xaf minus 0. This slope must be equal to the slope of the diagonal. What is the slope? 1 plus xaf y2 minus y1 minus 1 plus xa, so 1 minus xa divided by xa minus 0, that is xa minus 0, right? Okay, so let us solve this because xaf is known and I want to find the value of xa. So this 1 gets cancelled and xaf gets cancelled. On the left hand side I have the value of 1, and then 1 gets cancelled. This is xaf minus xa is equal, divided by xa is equal to 1. Xa goes here, becomes 2xa, and therefore you have the result that xa should be equal to xaf divided by 2. This is how a question can be asked. In fact, this question I was taking, so coincidentally this question I took from GATE because some similar kind of data is there. तो आपको ऐसा क्वेश्चन वहाँ मिलेगा. तो that is why I wanted to explain कि even ऐसे ग्राफ पे भी क्वेश्चन आ सकता है. आप ये नहीं बोलना कि सर ये तो पेपर में सॉल्व हो ही नहीं सकता, तो ऐसा क्वेश्चन आएगा नहीं. देखो ऐसा क्वेश्चन आ चुका है और इसको और भी अलग अलग वैरायटी से बनाया जा सकता है. अब यहाँ पे मैं आपको ये बस बताना चाह रहा हूँ कि इस मैक्सिमाइजेशन ऑफ रेक्टेंगल का ये जो मेथड है और मिनिमाइजेशन ऑफ टोटल वॉल्यूम का जो मेथड है, इससे रिलेटेड क्वेश्चन फ्रेम हो सकता है. कैसे करना है? व्हाट इज द कॉन्सेप्ट? द कॉन्सेप्ट सेज दैट द स्लोप ऑफ दिस and the slope of this should be same. मैंने बस same कर दिया. I have used the basic geometry. Just remember this concept, right? So this was about the qualitative analysis of the reactors combined in series. Further, more qualitative analysis is required that we are going to discuss definitely when the reactors are connected in series.